Now we prove alpha into infimum of S equal to supremum of alpha S if alpha is less than 0. It has two cases arises. Case 1, let S subset X which is unbounded below and alpha less than 0, which implies alpha S is unbounded above because alpha is less than 0. Before we discuss, if a set is bounded above, if you multiply negative quantity, then that set is bounded below. Since S is unbounded below and alpha is negative, then alpha S is unbounded above. Infimum of S equal to minus infinity and supremum of alpha S equal to plus infinity. Since alpha is less than 0, alpha into infimum of S equal to plus infinity and supremum of alpha S equal to plus infinity. From these two, we have alpha into infimum of S equal to supremum of alpha S if alpha is less than 0 and S is unbounded below. Now we prove alpha into infimum of S equal to supremum of alpha S if alpha is less than 0. The first part is over. Come to the second step, second case. Let S subset X which is bounded below and alpha is less than 0. Since S is bounded below and alpha less than 0, the alpha S is bounded above. Since the set of real number is complete, then any set which is bounded above, it must have a least upper bound. Any set which is bounded below, it must have the greatest lower bound. Since R is complete, then infimum of S and supremum of alpha S both are exist. Let B is equal to greatest lower bound of S, that is equal to infimum of S, and C is equal to the supremum of alpha S, that is equal to the least upper bound of alpha S. Now X greater than or equal to B for all X belongs to S. Why? Because B is the greatest lower bound, which implies alpha X is less than or equal to alpha B. What is the reason? Alpha is less than 0. When you multiply the negative quantity, the inequality reverses its order. That means every element of alpha S is less than or equal to alpha B. By definition of upper bound, alpha B is the upper bound of alpha S. Since C is the least upper bound of alpha S and alpha B is any upper bound of alpha S, then C less than or equal to alpha B. This is equation number 1. Now alpha X less than or equal to C implies X greater than or equal to alpha inverse C for all X belongs to S, which implies alpha inverse C is the lower bound of S, which implies B greater than or equal to alpha inverse C. The reason is B is the greatest lower bound of S, alpha inverse C is any lower bound of S. So greatest lower bound always equal to any lower bound. Now alpha B less than or equal to C because alpha is less than 0. From equation 1 and 2 we have alpha B equal to C. Alpha into infimum of S equal to supremum of alpha S when alpha is less than 0 and S is bounded below. That means my theorem is totally complete. Only we discuss only two corollaries.